again, the technique of what is called Newton's method is a technique to solve equations. And like, think about it, in algebra, you can solve quadratic equations easily, right? There's a formula there. You can solve linear equations easily. There's, you put everything on one side, the variables on the other side, etc. But what happens, excuse me, if you have an equation third degree or higher, or even equations that have like, not necessarily polynomials, but like trigonometric functions and things like that. For example, what if you had something like x cubed minus cosine x equals to 25 or something like this? We have no tools from algebra to solve this, right? Basically, by the time you get beyond quadratic equations, the techniques of algebra are really not very reliable. You have rational zeros theorem, etc., but they're not that good. They're not very efficient, etc. So today we're going to learn a method to solve higher degree equations. It's really amazing, and it's called Newton's method. And you had to know a little bit about calculus before you could study it. That's why we're introducing it at this point in the semester in a calculus class, and you couldn't have known this in an algebra class. So basically the idea will be the following. We're going to try to solve an equation of the form f of x is equal to 0. Because think about it, every equation can be put in that format, right? You put everything on one side, get 0 on the other side. What does it mean graphically to find the zeros of an equation? What does it mean to solve the equation f of x equals to 0? If you were to graph f of x, how would you pinpoint the zeros? Those would be the x-intercepts, right? So if you have a function, you're trying to solve this equation that is equivalent to saying find the x-intercepts of that function. So that's what we're going to try to do. We're going to try to find the x-intercepts of a given graph, or that really corresponds to solving the equation. Okay, in the next 10-15 minutes or so, we're going to derive this method by going, you see in your handouts, which is the same as what I have on the board, you have dotted lines. We're going to fill in the blanks. We're going to come up with a formula that will help us to solve equations. And once we have that formula determined, we're going to go and do some examples like the one I have on the top there. We're going to be able to solve these higher level equations. Again, it's really, really important because if you think about it, in a sense, everything in mathematics is an equation, because ultimately, in real life, people are trying to do things. When they're trying to do things, they write it in the form of an equation. So solving equations is such an important concept in mathematics. So this was a huge breakthrough. And again, the credit is given to the mathematician Newton. This is the same Newton with the falling apple, famous in physics. Still, he has also a lot of things, as you can see. He's given the credit, of course, for coming up with the ideas of calculus in the first place. Okay, so here's the general idea. Let's look at this graph. First, I'm going to give you a graphical idea, then we're going to dive into the equations and derive the formula. So let's say you have a function like this. This is your y equals f of x, this curve. And we're trying to solve the equation f of x equals to 0. So that amounts to finding this point right here, correct? The x-intercept. We're trying to find this point. And the way this method works is you begin with an initial guess. Okay? Here our initial guess is x sub 0. You take the initial guess, you plug it into the function. Right there, you draw the tangent line. So right there, you draw the tangent line. Do you notice that the x-intercept of that tangent line is now a little bit closer to the actual 0? So your initial guess was this much apart, right? Your initial guess was how far away from the actual solution, this far away, right? But the x-intercept of the tangent line is now only this far away, right? And then you repeat the method. This is called the method of iterations. You plug the number back into the function. Let me use another color for that one, say green. Okay, so we're going to go back into the function, draw a tangent line right there. And where it hits the x-axis, do you see now that point is a lot closer to the point we're trying to find? What point are we trying to find once again? The 0, the big red dot right there. So every time you draw a tangent line and look at the x-intercept, basically it's getting closer and closer to the original number we're trying to find. So the way this method is going to work, we're going to create a table of values. We're going to create a table of values. This is called iterative method or iterations. So we begin with initial guess. We're going to do something, get something else. Then we put that number in here, and then that's going to give us another number. We keep getting closer and closer to the actual 0. And when do you stop? When do you stop with the method of iterations? When two successive zeros are really, really close. How close? The problem will specify. Let's say you want accuracy to the nearest hundredths. So that means you're going to stop. Like if one solution is 3.99, and the other one is, let's say, you still get like 3.9948, something like this, that they're not changing that much. After a point, you see they're really close to each other, that's when we're going to stop the solution. Now, I actually saw a demonstration of this on the internet recently, so let me see if I can quickly show you that before we go ahead and derive the function. Let's see. So they have an equation here. So they say pick an initial guess. At the moment, you see they pick the initial guess of 5.3. Let's just pick our own initial guess. And how many zeros does this function have? It has 1 here, 1 here, 1 here. And depending on what your initial guess is, you're going to find 1 0 at a time. Okay? So let's pick an initial guess. So I'm going to pick like the number 10. And I'm going to click on draw tangent. Oh, first of all, restart at number 10. You see the line drawn. Okay, draw tangent. So at that point, draw the tangent line. Where the x-intercept of the tangent line is, it goes to the function. So now if I say draw tangent again, at that new point, it's going to draw a tangent line. You see already in 2 iterations, it's found pretty much the 0. You see it says 11.3. If I do it again, draw tangent, 11.37, draw tangent. It didn't change that much anymore. So it's already in 2 iterations, it got the answer. You give me, let's restart. You give me another initial guess. Where should we start? Just I want you to see a few of the drawings to get an idea what's happening here. How about like 1 or something like a smaller number? Say 1. Restart at 1. So it drew the blue line. Draw tangent. So it draws a tangent, and where the tangent crosses the x-axis, at that point, it goes to the function once again. So what is it going to do again? Draw another tangent at that point, and another one after that. Already you see it's at 3.34. If I draw a tangent again, it's already, the x-intercept is so close to that 0. Now it's 3.36, 3.369, it's not changing that much. It's already found a solution. Basically, the values has converged to the actual solution. Okay, so now we're going to do this by finding an equation. What is happening here? We're going to find a formula so we can apply this to all the problems. Yes, a question?
Go back there. Like on the 1 with the 3, it was below the function. Is that just negative now?
Sure, the function value is negative here.
Right, so let's click it again at 1 below.
Do a tangent.
Yes, it's like right underneath. That would be negative 2.9 something.
No, the x-coordinates here are positive. 0 is right here. The x-coordinates are all positive.
Oh, that's an x-coordinate?
Yes, these are right here. These are like 1, 2, 3, 4, 5, 10. These are the x-coordinates, and they're all positive. But they're getting closer and closer to the 0. But it's a little bit of a luck, as you can see. When you pick your initial guess, it's a little bit of a luck as to which of these zeros you're going to end up finding. But since there are computers used these days, you can quickly pick a lot of initial guesses and quickly comb through, and you can find all of them. But in this class, usually I might give you a suggestion saying, say if you're trying to find this 0, I might say, okay, pick an initial guess close to that 0 so that you're going to end up finding that solution. And like on a test, I might only ask you to find one of the zeros because it's going to be too much work to find all the zeros. Okay. So now we're going to derive our equation. Again, we're going to follow from your handout and fill in the blanks. Okay. So first we're going to pick an initial guess. We're starting right here. First we'll pick an initial guess. In the graph below, what number represents our initial guess? X sub 0. So let's fill in the first blank as X sub 0. We draw a tangent line to the graph of f at which point? Remember, the tangent line was drawn right here. We went to the function. That point is x sub 0 comma what? F of x sub 0. Again, the coordinates here are x sub 0 comma f of x sub 0. Find the x-intercept of the tangent line. So we go down, the blue line goes down. And what is the x-intercept of that tangent line that we just drew, the blue line? X sub 1, right? That's the next iteration. And note that x sub 1 is now closer to the x-intercept than the original initial guess was. I will draw a tangent line to the graph of f at which point? X sub 1 comma f of x sub 1. We call this the x-intercept of this tangent line. We're going to call it, that's the green line. What is the x-intercept of that green line? X sub 2. So you get the idea. Basically, we start with our initial point x sub 0, then we get x sub 1, then we get x sub 2, and we keep getting closer and closer to the actual solution. That is the idea. Okay, so continuing on from our handout, we are looking basically for an equation that will give us x sub 1 once we plug in x sub 0. It'll give us x sub 2 when we plug in x sub 1. So it keeps giving us the next point, basically. It's called the method of iterations. And we're going to repeat it until we get the desired accuracy. But how do we find this equation? That's the dilemma. Let's first form the equation of the tangent line through the point x sub 0 and f of x sub 0 with a slope of f prime of x sub 0, because that would be the equation of this line, this blue line here. First, we're going to try to write the equation of that blue line. And then we'll find the x-intercept of that blue line. So how do we write the equation of that line? Right, point slope form. So y minus, the y coordinate here is going to be f of x sub 0 equals the slope. The slope is the derivative at that point, which is f prime of x sub 0, times x minus something. X minus what? X sub 0, right? That was the x coordinate at that. So the tangent line was like this. And we know what that point is, x sub 0 for x sub 0, so we use that point. Now, we need to find the x-intercept of this line. X-intercept of this line. As a matter of fact, we know the x-intercept. It's x sub 1, right? When it hits the x-axis, that point was called x sub 1. So what we're going to do is we're going to replace xy with x sub 1 comma 0. In other words, we know that this point is a point on that line, is it not? That x-intercept, x sub 1 comma 0. So in the previous equation, replace x with x sub 1 and y with 0, because we know that is a point on the line. So replace y with 0. And replace x with what? X sub 1. So what I have done, let me use again a different color here. What I have done is instead of x, I put x sub 1. Instead of y, I put 0. Why did I do this? Because I know the point x sub 1 comma 0 is the x-intercept of this tangent line. So I know it's a point on that tangent line. So it must satisfy that equation. So when y is 0 and x is x1, it's a point on the line. It must satisfy this equation. So I substitute them in. And remember, we're looking for an equation now. Basically, if you could tell me what x sub 1 is in terms of x sub 0, that's a huge breakthrough, because from there we can get x sub 2 in terms of x sub 1, and we can do our iterations. So the big step right now is, can we get x sub 1 in terms of x sub 0? Can we have an equation for that? So can we solve basically for x sub 1 here? Okay, to solve for x sub 1, let me first divide both sides by f prime of x sub 0. I want to get rid of that factor there. So let's divide both sides by that. So here you already have negative f of x sub 0, right? I'm dividing both sides by f prime of x sub 0. So what does that leave me with on the right-hand side? You divided both sides by f prime of x sub 0, right? So the first expression there is gone, right? This is gone. So what is left then? X sub 1 minus x sub 0 is left there. Remember, I want to solve for x sub 1 in terms of x sub 0. So there's just one step left. If I want x sub 1 right now, what should I be doing? Add x sub 0 to both sides. So if I'm going to add x sub 0, it goes over here as positive x sub 0. And don't forget there's a minus f of x sub 0 over f prime of x sub 0. Basically, this was the next step in your notes. It said solve for the x sub 1, which I've already done it over here. But in your notes it says, okay, solve for x sub 1, get an equation. Okay, now this gives you x sub 1 in terms of x sub 0. But in your notes I also asked you, in general, can you give me x sub n plus 1 in terms of x sub n? Because if you could do that, then from any point to the next one, you're going to go with ease, okay? So if this is going from x sub 0 to x sub 1, I need to know, and I can even put it right here, what will x sub n plus 1 be in terms of x sub n? Any thoughts? X sub n minus f of x sub n divided by f prime of x sub n. How do we do it? We just looked over here. When you had a 0 subscript on the left side, you had a 1 subscript on the right side, right? So now if you have an n plus 1 subscript on the right-hand side, you're going to have a subscript of n on the left-hand side. So that actually gives you the general formula that we need for the Newton's method. What you see here, ladies and gentlemen, this is it. This is the formula that Newton came up with to solve equations of any order, any degree, even trigonometric, even logarithmic equations. But there is a catch. Unfortunately, there are times when this method doesn't work. It works most of the time, but there are situations where, like there are graphs, something like this. You go to the function, you draw a tangent line, like you get here. Then you go to the function, you draw a tangent line, you get here. So sometimes it goes in a loop. It keeps coming up, like going back and forth, the same tangent line, the same tangent line. It never converges. But this occurs rarely, so this method is still really good. It's not 100% good, but it works in most situations. And after Newton, other mathematicians came by, and they even created better methods than Newton's method. So now there are other iterative methods, which you might take in a class called numerical analysis. Like if you're an engineering major, you may take that class. But in this class, we just look at one basic model, one basic technique to solve equations using iterative techniques. Okay, so we're going to use this formula now to solve some examples. And so after some examples using Newton's method, okay, let's start with this example right here. X cubed plus 3x plus 1. And as you can see already, and it looks like a simple equation, but techniques of algebra would be very limited here. You would have a hard time. You could do rational zeros, but what if the zero was not rational, like square root of 3? Even rational zeros theorem would have failed. But this method is much better. Now, the main question becomes, how do we come up with an initial guess? And for that, I'm going to let you guys use your calculator, graph the function, see where the x-intercept is. Say if it's between 1 and 2, for example, you may want to pick 1 as your initial guess, okay? So let's go ahead and to the calculator and graph x cubed plus 3x plus 1. Go to your y equals screen and enter x cubed plus 3x plus 3x plus 1. And let's take a look at the graph by looking at zoom 6 as a standard viewing rectangle. So it looks like there might be a 0 there. We can do better than that. Say window, x min. Let me go from like -2 to 2 in this case. So we see that there's a 0 between -1 and 0, correct? So I could start with -1 as my initial guess. But you will see that you could start with many different values, especially if there's only one solution. You will still end up with the same correct solution. So you don't have to begin with one number. Some people could start with -1. Others could start with +2. And if you like, try that. Like if I'm going to start, let's say, with -1 right now, you guys could start with +1 or +2. The only difference might be that some of you may have more steps until you converge to the actual solution. I may have 3 steps. You may have 5 steps. But ultimately, we'll all come up with the same solution. Okay, so in this case, I'm going to start with -1 based on the graph. So we're going to do a table of values here. Okay. So your handout already has it. Okay, in your handout, looks like I started with the initial guess of 1 there. Again, it really shouldn't matter where we begin. We could also start with 1. So I guess I'm gonna stick with what you have in your handout. It said that we're going to start with 1, so let me go with it. But it's, like I said, you could have started with -1, you could start with +2. It really doesn't matter that much. Ultimately, you'll still come up with the same answer. As a matter of fact, I will illustrate that to you in a little bit. I'll pick 2 different initial guesses and show you that we come up with the same final result. For this one, let's begin with the point 1 as our initial guess. Okay. Then, again, since this is the formula, what you need to do is you need to evaluate what f of x is. In this case, f of x is the given function, which is x cubed plus 3x plus 1 at that point. Then you need to evaluate, since the formula has f prime in it, what is f prime for this function? F prime is 3x squared plus 3, right? So then you need to put your f prime into your table. So in this case, f prime is 3x squared plus 3. And then the entire formula, which is x minus f of x over f prime of x. I just dropped the subscript to make it less cumbersome. Okay, so basically we're starting with our x sub 0. We're going to plug it in into the function, to the formula. That will give us x sub 1. Once we have it, we'll put it into our second row, and we'll proceed the same way, okay? So let's begin. Find out what is f of 1. If x is 1, f of 1 is 5. Just plug it into the f of x function, right? Okay, what about f prime of 1? 6. What about the last step? So that will be 1 minus 5 over 6. Which is 1/6, right? 6 over 6 minus 5 over 6 is 1/6. Let's get it as a decimal because we're going to have to plug it into the function in the next step. Again, if you like, you could keep it as a fraction as 1 over 6 or use as a decimal as 0.166. Let's say in the intermediate steps, use at least 4 decimals. And I need to tell you how many iterations we're going to go. Let's say that we want the answer, and it's in your handout, it says we want the answer with an error less than, we want the error to be less than 0.001. So we're going to continue this step until 2 successive iterations are less than 0.001 apart. Okay, so now let's continue. Take that value you got there, which was 1/6 or 0.16666. Now plug it into the f of x function. Your f of x function is already in your y equals screen, is it not? So what is the easiest way to plug something into your function? Go to table, right? It's already y, it's already in there. So go to your table and delete what you had originally. And I'm going to put exactly 1 over 6 here for x. So the function value there is 1.5046. 1.5046. Okay, and how about f prime? You know what we can do? We can actually go to y equals, because this is going to be helpful in the next few steps. Go ahead and put f prime into your y sub 2. So in this case, 3x squared plus 3. And if you go to now table, it will tell you what happened at x equals 1/6. y1 gives you what f of x is at that point, and what does y sub 2 give you? What does the 3.0833 indicate? .0833. Basically, if you plugged 0.1666 into the derivative function, you would get 3.08333. You could do it by hand. You don't even need a table. It's just table is saving you some time, as you can see here. Okay. Now, for the third column, we could do this one by hand. Do x minus f over f prime. So 0.1666 minus 1.5046 divided by 3.0833. And what do we get for that? negative 0.3213 roughly. Do you remember what the solution was to this equation? It was between what and what? Remember the graph, what the graph looked like when we looked at it a minute ago? It was something like this, right? The solution was between -1 and 0, right? So already we have a closer answer. Negative 0.32 is already closer to the actual solution than was +1. Now if we repeat it one more time, we're going to get even closer, okay? So now I want you to put negative 0.3213 in the first column. And now that we have a nice table set up, this will be very easy. So I just came down to the second row and I entered my new x value, my new iteration. If you press enter, enter the x value and press enter, automatically it evaluates for you the function and the first derivative at that point. Do we see that? Again, just remember what y1 is. y1 is your function and y2 is your derivative stored in the calculator. So y1 is 0.00293. 0.00293. Could you tell me what f prime is? Thank you. And now let's do x minus f over f prime. So do this number minus so negative 0.3213 minus f over f prime based on the formula, right? F here is 0.00293 over f prime, which is 3.3097. Let's see what this says. Okay, anybody who got something? Ryan, negative 0.3221. You see, we're now even closer to the actual solution. And you see that it's starting to converge now. You see how little the answer changed from this step to that step? Here, the first two decimals were negative 0.32. The second decimals are negative 0.32. So we already had the answer to the nearest hundredths accuracy, basically. But we want to the nearest thousandths accuracy. So let's just do it one more step. So usually we're going to stop when the first three digits match, when the first three digits are not changing. So very simply now, just bring the new number down. So now negative 0.3221. And I'm not going to put the intermediate steps right now. I just want you to tell me, what do you get in the last step if you do the new number? Negative 0.3222. Okay, so now we're in agreement. The first three decimals here and here match. And that's where I'm going to stop. And I'm going to say the x-intercept for this equation, or the solution to the given equation, is negative 0.322. And you can go back to the graphing calculator and verify this, of course. And to make things even easier for you, I'm going to also show you one more nice feature of the calculator. You see how we did the last column by hand, right? We did x minus f over f prime. You could have made the calculator do that last column also. So we can go back to your y equals screen. So go to y equals screen. What do you think I should enter for my y sub 3? Exactly, Madeline. X minus y1 over y2. How do you enter it here? Like this. X minus. Does anybody know how to get a y1? You know, if you don't know how to get a y1, you could open a parenthesis and enter the entire function, close the parentheses, divide it by, put the other function down there. But the shortcut notations will make it easier for you. So how do you get a y1? Go to vars menu, y vars. Number 1 is function. Number 1 is y1. Division sign. Let's do it again. Now I want to get a y2 in there, right? How will I get a y2 in there? Same way. Go to vars, y vars, function, but this time I want a y2 in there. So now if I go to my table, and if you scroll over to the right, it's even going to give you what the y3 is. So all you have to do is take the y3 and put it back into the first entry of the next row. But basically, it's going to give you even the third column in there. See, now that we have this nice table set up, let me illustrate something to you guys. Earlier, I said that no matter what value you start with, you should end up with the same x-intercept, right? So let's go back and start with a different initial guess then. For this question, we started with 1. Then 1 gave us the 0.16667. Let me start with -1, see what happens. -1. Okay, so I'm going to go all the way to the end of that row. I get -0.5. So I'm going to come back and put it in here. -0.5. Press enter. Sorry, that's my hyper pen here. Okay, -0.15 here. Okay, press enter. So go to the end. What do we get? -0.3333. I'll go back and put that in there. -0.3333. And what does that give me? -0.3222. So you see we're close already, and we start with a different initial guess, so it's giving us the same number, right? So take that one, put back. You get the idea. You'll get the same exact solution, even if you start with a different value. There is one danger, though. Sometimes, very rarely, you start with an initial guess, and you get to this level, you get to your f prime, and you get a 0. What is the problem with that? Do you see what the problem will be in the next step? You have to divide by 0, which cannot be done. If you ever have that situation, go back and pick another initial guess, okay, if you end up with a 0 in your f prime column, okay? So now I'm going to give you guys another example to solve. And now that you have this nice table created, it's just a piece of cake, right? Let's see, which one do I want? Okay, let's do this one, and I want to give you some time on it. So for this question, we need to start by putting everything on one side and get 0 on the other side, right? So this is our f of x. So what about f prime? The derivative is 4 over 2, or 2x cubed minus 3. That's our f prime. And the last column, of course, always is going to be x minus f over f prime. And we looked at the graph on this one. By the way, I've already entered the y1 and y2 in here. But when you're first looking at the graph, what I was suggesting to you was turn off the second and the third ones. Otherwise, it'll overcrowd your graph. How do you turn it off? Put the cursor on the equal sign and press enter. It turns it off. I also want to turn off the third one. Put the cursor on the equal sign and press enter. Now, only the first one is selected, and I can graph this. And I may have zoomed in a little bit to see it better. Actually, let me go to zoom standard, say zoom 6. So it looks like it has 2 x-intercepts. In this one, I want to specify find a positive solution. For some questions, I asked you to find both of them. If you are to find both of them, you have to create 2 separate tables with 2 different initial guesses, right? So I'm going to find a positive one. And as I mentioned to you earlier, I started with 1. But this is what happened when I start with 1. First, let me go to the table and clear the past entries. Oh, you see I turned it off. Now it doesn't show here either. I better go back and turn them back on. Press enter on the equal sign. Enter on the equal sign. Okay, on the table, now they will show up. So if I start with 1, I ended up with negative on the third column on y sub 3. And I knew this was going to start looking for the negative root. So I was determined to find the positive root first. So I came back, and I remember from the graph, if you go a little bit to the right, you end up with a positive slope on the curve. So instead, I started with 1.5. So if I go to y3 now, that was positive, 2.825. Take that, come on down. 2.825 is my new iteration. This is my x sub 1. My x sub 0 was 1.5. And again, we can go to the end, see what's there. 2.341 was the next. 2.341. And if you look at the end there, 2.1206. This one's taking a little bit longer, but it's okay. What was it? 2.1206. Thank you. And so you guys, 2.074. We're almost there. 2.074. And finally, this is the last one, 2.072. Take it one more time. 2.072. Except don't put two dots in there. There we go. So if we go to the end, we have it. Now sometimes what I'll ask you is when you copy your solutions, give me the first row, the last row, and the last column. Give me all the entries of the last column. That way, if you made a mistake somewhere, I still have some of your work. I can try to give you some partial credit, try to figure out what happened. But then you don't have to copy every single number there. So here, one moment, please. Here, I start with 1.5. I'm going to put the first row in there. But I'm not going to enter every single, excuse me, Y1 was negative 4.969. Y2 was 3.75. And Y3 was 2.825. So I'm just going to now write down the third column, copying from the calculator. And again, why am I stopping at this level? Basically, I want, right, accuracy to the nearest thousand. So when they start repeating themselves, that's when I stop. And again, ideally, I would also want you to write down the entries of the last row here. This one is almost 0. And the only other hint I want to give you is if you have a trigonometric function, like in your handout you have one with cosine function, make sure that you are in radian mode in your calculator, because this process uses the derivative, right? You have in the formula f prime of x. Anytime you take the derivative of a trigonometric function, know that somehow in the process you assume the function was in the radian mode, basically. And some of you got the negative solution. Let's also write that down, so if somebody wants to do that, they can check their answer. What did you get for the other solution, the negative one? 0.8937. Would everybody agree? Okay, great. Pardon me, Sandra, did you get something? Can you guys double check this one, because I did not do this one. Did you all get the same thing? Okay, great.